Good, and I can start. You feel free to interrupt me anytime, especially we are in a smaller group, so there should not be too much, people being shy. As the first thing, of course, I want to thank you on my side for this invitation, for this surprise. Very experimental for me, because it's something that we have done in the last few years, and then we wrote a paper, and now I think it's the first time that I presented. So I have to actually, when you present, you have to really organize in a way that is different. What I thought to do is present some. I wasn't sure exactly how the audience is, but I thought to do something that is not only about OpenBIS. You give me a lot of time. I talk a lot usually, but maybe I will speak so long, but I'll try to stay a little bit shorter. What I thought to do is to not only discuss of OpenBIS, first give some introductory concept that I would have been happy to have somebody that would explain me this thing before I start like a typical scientist. Yeah, I know, I start doing things. And then you realize that certain things are, you need to know certain concept. So, and let's start. So this is the organization. I have 3 modules, let's say plus conclusion, a little bit of motivation, why we have done these things. Why do I have to manage that? Most probably I overlap things that have been already presented before. I'm not sure. So feel free always to wave your hand if I'm saying something that is already boring, because you know already. And then I put my own personal 7 concepts for tool deployment. So there are tools. The one I discuss here is called OpenBIS. But before, as I was saying before, using it, you should have clear in mind what I try to reduce to 7 concepts. And then I give you this real world example. And then the 10 commandments, I call them like this, of the digital. So let's start with the motivation. And I will start with a video. So, okay, so I start this video. You see, you hear now? Okay. We are now in the NASA.
Clear. Break, buzz, this is Houston. Radio check and verified TV circuit breaker in. Roger, TV circuit breakers in. Page 5 clear. Roger. And we're getting a picture on the TV. Okay. You got a good picture, huh? There's a great deal of contrast in it, and currently it's upside down on our monitor, but we can make out a fair amount of detail. Okay, Neil, we can see you coming down the ladder now. Neil, we can see you coming. Yeah, I'm going to step off the limb now. That's one small step for man.
Almost finished, not 1 hour.
Giant leap for mankind. How is the quality of the TV? Oh, it's beautiful, Mike. It really is. Oh, geez, that's great. Is the lighting halfway decent? Yes, indeed. They've got the flag up now, and you can see the stars and stripes on the lunar surface. Up now, and you can see the stars and stripes on the lunar surface. Beautiful, just beautiful.
Oops, no, I will not show again. Why I show this video? Of course, you recognize this video. Most probably, most of you have seen. I don't think nobody here in the things have experienced this live. This was July 20, 1969, when the American landed, Armstrong landed on the moon. And this video has been shown over and over again. But I was surprised to discover in this book that I see there that this video is lost. Nobody has this video anymore. The original high-resolution tapes of the Apollo 11 was lost. It's gone. And this emerged in 2006 when a professor tried to find the original tapes, but this video was lost. So it was going all over the continent and trying to see from televisions, from broadcast, pieces of them, and then put together this, what you see, the low resolution video, which we thought, okay, in the past they didn't have the quality, but actually tape was one of the best way to store. And in the end, another professor, this is mentioned there, it's somebody that has strong hints that the same tape were reused to record other stuff. So people just use the same tape to store other videos, so the original epochal things of the things is lost. This is, I think, the strongest for me visualization of why we need to manage data. I wrote there in memory of data loss. If you want to have the full story, now I made it short. In this book, it's very nice. It's given with full detail. This book I have now in front of me. That's why I was making sure that I tell you the right things. And I extracted two information that the book is not the newest one. Now it's 10 years old, 2015. That 31% of all PC users have suffered complete data loss. I hope nobody here to me happened, but the most extreme case I've seen was a PhD student that one day before submitting a thesis was a lady, a computer was stolen in Zurich. She went on a bar and then she looked, where is the backpack? The backpack was gone. And then she never found this. She didn't have any backup, nothing. So there was a terrible story with the PhD. And an estimation is that 17%, so 1 every 6, if I'm not mistaken, of the data that are acquired are lost every year. So there is a need to do something. And this is not, is one half of the story. First of all, before I tell you the other half of the story, what are data? Most people know here, but it's important also for discussing about OpenBIS, because OpenBIS being a computer, it doesn't understand, it doesn't have the flexibility that the human mind has. So I define raw data that are directly acquired from the instrument, that are not processed. The primary data are clean, calibrated, and transformed. Secondary is a little bit of interpretation, modeling, typically you do with the post-processing, origin, or whatever. Then there is documentation, might be the paper. And then on the other side, people speak a lot about metadata. Now, among metadata, we have to distinguish between plain metadata. We can define also in OpenBIS species, colon, mouse. OpenBIS was originally used for biological, in fact, OpenBIS is biology information system. But the computer would not know what a mouse is, might even think that this is the mouse. So actually you should have a certain little bit more, people say, semantic way. And in biology, they use this kind of library. So if you would click now on this, you would land on a database where the mouse is defined. And so define the metadata. This sketch is also important for sometimes resolving questions that in a lab people might have. I experienced myself, one PhD student acquires some data and the other maybe, or one bachelor student, one master student working with a PhD student, and the PhD student say, can I use this in my thesis? Actually was acquired by the master student. And I'm not sure if there is an official line, but what I always say, raw data actually belong to the organization. It's maybe the secondary data where actually the person, the student, and made his own interpretation, analysis, plotting, and things, that there is a certain proprietary character. Okay, I think this is quite obvious. If you have a question, interrupt me. And then allow me, I make a parallelism with biology. In biology, there is experimental law that has been discovered by Professor Kleiber, that was professor at ETH in Zurich. And he took data of animals of their size and on the metabolic rate, so how much energy actually they consume per hour. The data are plotted there, and he discovered that all this data scatter a little bit, but in a logarithmic scale tends to follow a line, and actually there are 3 lines, and he could define categories of animal. So basically what he was saying is that the metabolic rate scales with mass. When I read this, I thought, oh, it's very interesting. How is it with instrument? Does a big instrument consume and produce more data? Or maybe a small instrument, a pH meter, maybe it's more complicated. I thought as a game, I took the student, we went through the lab, and I asked them to prepare a similar plot with data from the instrument. So these are the instruments that we had in the lab and the different techniques. And this is the kilobytes per single run. So we just went over, I think, 10 years of the period that we measure, and I see how big are the files that from this instrument. I'm not sure if all of you are familiar with all these acronyms. I will not go through all of them. Just consider these are different animals in the lab. Okay, so this I consider the genome. So to generate an unit of information, which is the file, which is the run, how much bits this instrument produce, how much data this produce. This is the raw information, going back to my sketch. And then I say, okay, let's look what the student, the technician, and the people do with it. How do they metabolize it? How do they digest and extract information? And so I simply look at what was generated, and I was very surprised to see also, like Leiber's law, 3 categories. There is some case which I call anabolic, that on a basic blue, the raw amount of data, the generation of plot is typically generate files are much bigger than that. So then it's much more kilobytes per day. There is a category more or less remain the same, but there is a third category where actually the raw data are much bigger than the secondary data. This was a bit surprising. I will tell you in a second why. And then I plot like Leiber's law. This is a little bit also as a game with a group, just to, it's a little bit nerdy thing in the group. And then the raw data was on the x-axis, and then I define here on the y-axis the metabolism of these things, and then I found the 3 categories. Now, why some instrument produce data that are, let's say, smaller, but once you process them, they become even smaller than that. This is surprising. How can data self-destroy? And then I discovered this. It took a little bit of detective work. And I realized that it was in particular with this blue, what I call catabolic, that the technician there was running a full scan, full time, full spectrum, simultaneous, so getting the entire range of compounds that were in the sample. But in the end, he was interested in one or the other, or 2 peaks in 1 or 2 compounds that for his own purpose, for his own service was important. So he was extracting the information about these 2 peaks, and all the rest was throwing away. Throwing away doesn't mean it was destroying. It was remaining as raw data in the database, but actually in the processing phase, it was using only these 2-3 peaks that it was interesting. This is interesting also to learn that actually sometimes we measure much more than actually we need for the information, because data and information are not exactly the same. And this is the second half of the motivation, not only because data are lost, as I said in the beginning, but also because labs produce more data than ever. I just show you what happened with the animals in the lab I was before. And then the manual system are insufficient to manage all this. In 2010, The Economist made an article, actually cover page, the data deluge. So means that we are going to be overwhelmed by data. In 2010, we were producing only 2 zettabyte of data. This is a more recent statistic with extrapolation in the future. If you see here nowadays actually we are producing how much? Almost 100 times more. And then the projection is that in about 2035 we will produce 1,000 times more. So this thing is not going to be under control. Also, if you think about how many pictures you can do with your mobile, how many selfie, how many things, and posting, all this data is going to be present somehow. And I'm not sure that there is much information that from the many picture and selfie I do with my family that make the world a better place. So there should be a way to organize this data. So this was my motivation. I'm pretty sure this is familiar for everybody. I don't know if you want to make comments and add something before I go discussing on the concept. Should I simply go ahead?
Yeah. I think so. There is no question in the chat yet.
Okay. So then I said, okay, good. Then there was a good thing to have an instrument, a tool. An instrument now is more a software, it's not a machine, that is used to organize this. But I will tell you already the conclusion of this study, that there is no one single instrument, and there is no instrument that fits all sides. One size fits all is at the moment not possible. And the third thing that is very important, certain things you have to know from certain information, the concept that I give you, the 7 concepts, clear from the beginning in order to make the process more efficient. So let's look at these 7 concepts. And the first is that there is a data life cycle. And the data life cycle quite obviously start with planning. I don't know if this is obvious because many people don't plan. They start measuring and only after, even myself, and only after try to see, oh, what do I do in the data? But I thought typically it's very boring and annoying to plan exactly all the measurement that I have to do. Typically, I'm forced to do as I wrote there when I submit proposal, because a funding agency want to know exactly what data are you measuring, does it make sense? And this is something that I hate, because how can I know before? What do I do? Then acquire. Then process, so we acquire, I get the raw data, you learn it now, process, I get primary data, then analyze, interpret for the secondary data. Typically, I document in the form of a paper, of a report for a customer or whatever. What should be more and more in the coming year is 6, 7, and 8, so preserve, share, and reuse. And in fact, I ask also ChatGPT, this you see is a screenshot for ChatGPT, how much each of these steps in the past, whatever ChatGPT understands as a past, present, and future, was important. So these numbers are given to me by ChatGPT. Maybe in different labs it's different proportion, but it's interesting to observe now. To read the table is a little bit more difficult. It's better I made a plot out of it. And for on the x-axis, the different phases and the time effort that ChatGPT evaluated in the past, in the present, and in the future. Quite interesting. The planning is getting 3 times more intensive. Most probably in the future, we should do much more planning before starting. But on the other side, acquiring it is extremely fast, much faster. You say 1/3 of the total effort than it used to be in the past. The processing, the analyzing, more or less remain always the same. And my interpretation of this is because there are attempts to delegate this to artificial intelligence, but still, as an expert, you have to do. I mean, if I would be confronted with corrosion data, not being an expert in corrosion, and simply because I say I have ChatGPT, they will tell me, I'm not sure how good will be my presentation in the top corrosion conference. So this is an experiment that somebody that is courageous could try, but I think will embarrass himself. So still, I think this process will remain a little bit more human. The documentation maybe will grow because it's not only writing the paper, it's also writing all the things that have been done. And this is, I anticipate already now in the introduction of OpenBIS, was one of the major problems, especially with technicians, because no, I'm busy, I cannot do all these things, these additional work brings nothing. But if people don't document everything that they've done, I will come back to this point later, then it becomes more difficult. Then preserve, share, sharing, I will discuss this in a slide, and reuse. I'm not sure this, I'm curious to see how many of you go to external database, don't measure your data, and use data from other people, which in the culture I grew up was considered stealing. But nowadays, the more open community is considered actually open science. I will come to this point. Most probably you have seen this already in previous slide. Tell yes or no. Yes?
Yes. Not exactly this one, but yes.
Okay, so I'm not sure I have to go too much into details, but this is the policy that organization try to encourage, they want to say enforce, that the data are fair, so I don't need to explain you what is findable, accessible, interoperable, and reusable. This graphic, I like it because explain not only what it means, that what we can do, because for me it's okay, findable, but how can I comply with that? So you get the slide and you can look Now, what does it mean, open science? The open science is the concept number 3. Beyond the policy is the ownership. In general speak, is quite trivial. There are two extremes. No? Data becomes or are public, data are proprietary. So open science or not open science. Open science actually is not new. Even in 1680, I found this letter in the internet of a scientist, now forgot who was. I prepared this presentation during the weeks, so this was one of the first slides I prepared. I have to check, I apologize. That he was writing to one of his estimated colleagues, sharing his insights. And the first time that this thing changes when people say, okay, but maybe it would be good to disseminate this more than one-to-one. And then was the first journal that emerged. The journal, it was a philosophical transaction in England, the Royal Society in 1666. 65, I see there also, decided that the people would submit their letter or their article, and everybody that was in the society, of course, it was also a little bit elitary and close, could read and post comment. So this is still like this. I mean, this looks very old, but this is somehow the way we do now. We share the data in the form of paper, not directly as a data, although there is more pressure and push to submit the data in a database. And I was discussing with a colleague while preparing this presentation, and then he gave me a very good idea. Look, nowadays we are all keen, and then we get position if our paper are cited. But he said to me, maybe in the future, people has to prepare databases to show that they have valuable, good data. And if people cite their database from Blind database from Ott, well, your reputation as a scientist goes up. And then I said, that's a great idea. I told him why people is not doing. He's retired, by the way, and he's now doing this. He's trying to bring a little bit more this thing. And he say, actually point to me to this article. Researcher actually refused to share the data. They said, this is my data. I don't want other people. They just come, take the data, and maybe they get a Nobel Prize with my own measurement. So the resistance is there. And we have to find a solution, an incentive to make sure that the people share the data, that they have return and they have the benefit. We can discuss this at the moment. I don't have, and I don't want to give a solution. But on the other side, there is a normal way of keeping data close. It's because companies, of course, they want to protect their competitive advantage. Nowadays, in the organization that I work, there is that I used to work. There are more and more people coming from the industry. And one of the first meeting I had with one of the new person, they asked me, why are you making papers, actually paper stuff for university? You are giving away ideas and people can take of it. So this mentality actually is okay, is there for businesses. But for scientific, now the trend is, although this is not easy to settle, is to make data, primary data, no, actually raw data, public. This is concept number 3. And this actually is not new. There are already, and I use data from other. I don't know from which community you are, but in spectroscopy, and I know also in astronomy, astrophysics, they connect to the NIST, so the National Institute of Standard of Technology in the US, and they have a number of databases. And we get databases from them because they are standardized, they are reference, and then to match our results. Now, I was surprised, another colleague in US told me that actually almost all the funding there is disappearing, and that is only political statement I meant. I hope there is nobody in US that will report this, but this is a fact that was on the news, that actually there is a risk that this thing will close, or if not has already closed, right now it's not maintained anymore. This is a static database that stays there. People can upload and put their own data for the benefit of other people, but there are dynamic database. Maybe many of you, especially those of you that live in Switzerland, do this daily. Connect to the website of Meteo Switzerland and look the weather. And this quite obviously is nothing but a collection of plots of table that are visualized on the meteorological situation, and you can you can look on your telephone. How is it possible that you can connect without complicated login, password, and stuff like that? This happens because you registered, of course, and because you have an so-called API. An API is my fourth concept, sorry. And I want to introduce, I'm not sure if you already know what is this, but application, I didn't know at that time, so I learned this is very important because you want to make sure that the instruments that are in your lab produce data and this data do not remain there, are uploaded in a database without too much trouble. And API is a set of rules that allows different software applications to communicate. Of course, each instrument manufacturer has his own standard. And usually I explain this to students with this analogy of the restaurant. This is you, this is the menu, and this is the waiter. The very first thing I do, or I expect actually, when I enter in a restaurant is to see a menu. Nowadays, you have to scan a QR code, and this bothers me because I'm a little bit old-fashioned. But sometimes in some small restaurant, in some places, not in Switzerland, but in other countries, the waiters come and tells you what they offer. And for me, it's annoying. I want to have a menu because the menu is actually the interface. I want to have my time, and I want to know what is possible. And then I tell to the waiter, and the waiter is my API, and bring this to the kitchen. The kitchen process the request and then give me the result, actually. Now, API is one way of communicating, but at the moment there is no standardized type for the data. Again, each manufacturer has his own data, and if I take, my colleague also said that if he rents a car, he enters there, his mobile connects immediately, can have his own playlist, and it's no problem. This system is not yet so for laboratory instrument, which is incredible, 500,000 instrument, and you have so much trouble, hire a postdoc, a technician to make sure that actually you get the data out of that machine. And there are organizations now I refer to the case in Germany, but I'm pretty sure, and I know that there are other organizations. This Allotrope is an organization that it's a foundation actually that is trying to develop a single universal data format. And the principle is relatively simple. It's just a translator. It's just like this lady would be in a lab and translate the language of every collaborator that is in the lab to the language you understand. This standard, this software that they use based on a so-called OPC, which is the platform that they use, permits to the instrument to communicate. Now, I didn't want to be too technical, but I want to just a little bit trigger curiosity. Of course, you can Google and go, and then there is a lot of information. One thing I think I have to still do, because I might have confused some of you, what is APC and what is OPC, no? And this I made also with ChatGPT. This is a nice visual. Okay, you imagine you have a sensor, and this sensor generates raw data, and the OPC makes sure, the translator, that this goes to your server, and this is stored in a way that is not standardized or a binary from that particular manufacturer, such that the API that you have can communicate with the cloud. So in this table, I show that actually both of them are for data communication, but while OPC works more on the level of devices and software for the automation, API helps the communication between software components, so in the end user. So it's more on the internal logic, where the other is make sure that the hardware can communicate. So in a simple way, I have to make several prompts. ChatGPT will give me a table that is so, for me, easy. Before it was a little bit more complicated. OPC standardizes how data is exchanged, and the other how services are used. So remember, the weather is more an API, but on the background, there are a lot of sensors that are in the sky and on the earth, and then they communicate. And the key difference is that OPC is mainly for industrial automation, but still in a lab. If you have OpenBIS, you want that the instrument automatically give the data in the database. You don't have to manually transfer. where the API helps you a little bit more general software development. Then there are different technology base. I will go a little bit more quickly, and then the different communication style. Okay, concept 5. Another word that I keep on hearing is ontologies. I don't know if you discussed this already before, then in that case I don't need to say. When I was a student in high school, I learned ontology was a philosophical concept that was related to the soul, to the entity of the human, of the concept. But in data science now, ontologies used to define the structure framework to formally represent knowledge. Basically, you have to define what you have in the lab, what kind of concept, what kind of instrument, what kind of device. I will visualize this more and more because exactly this is what you have to put into OpenBIS. So concept, relationship, properties, and rules. And why are they useful? I asked ChatGPT. This was a little bit interactive. I thought it was good because of standardization. If everybody actually give his own name to the same instrument, if somebody calls it Raman, if somebody calls Lab 503 and the other call is, I don't know, inelastic scattering instrument, then it's always the same stuff. Then it's difficult to combine this data. And when I say everybody can be also user of the same group, of the same lab. So in the end, the data becomes very chaotic, unmanageable. And the interoperability, that was one of the fair word, it's not guaranteed. The machine cannot read the data, and the integration becomes also more difficult. That's why you have to sit together with the whole lab, or depending on the actually policy you have in the lab. If you are a little bit more dictatorial, you decide for the entire lab. Usually I sit together and I ask, because then the best idea and the different flavor of the different needs are emerging, and this I recommend to do, because it might last a longer period of time to do a review like this, a brainstorming like this. But in the end, if the people work with you, then people is happy. Otherwise, they will make resistance. In the end, you will have a faster way of deciding things if you decide everything by your own, but a much longer period to make the things really operating in the lab, because the people is totally frustrated. And here I put a little example, but you can read it, you can look at this in the recording, in the slide. Concept number 6, one more to go. And this is the most complex I could figure out workflow in an analytical lab. Of course, this is, I would say, almost paranoid, because in specific lab, you have only subset of this. Plan analysis, prepare sample, submit the sample, acquire the instrumentation. In some cases, the procedure that you use are less than that. So rule number 1, always spend time to define what is the workflow that you want to map, that you want to image with your instrument database. Because otherwise, if it's not clear of this, then there are always things that pop out, oh, this is not the thought of, and then the data are a little bit not organized well. You have to make sure also that the data are following the workflow that fits for your lab, such that you can track and you can trace where the data have generated and so on. And the second thing that I want to, so spend time in designing. The second thing is that in reality is that it's not one single person make the whole story, no? Typically you have a group, and you have technician, you have PhD student, you have assistants, you have postdoc, and all these people contribute. So you have different people that contribute, and also in the time dimension. Now think about fluctuation in the lab, PhD student finish, another PhD student come, and so on. So this makes a little bit more unmanageable if you have this situation. First of all, the people have to stick to the rules that you have defined. So ideally it would be like this, but this is not true. And so what to do to try to account, and typically if you take the case of PhD student make code or processing, and they know what they're doing. But then after they leave, nobody knows their code, their instrument, and the thing. So how to solve this problem? In this, I discovered that the Swiss Data Science Center is an organization that is between ETH, EPFL, Lausanne, that is relatively young and dynamic, developed another software that is called Renku. And Renku is exactly for this problem. This is free, it's something parallel to OpenBIS. I try to work with them to integrate this in OpenBIS. Basically, you see here different nodes, different buckets of data stores, and then you have person that like I showed you before that manage this, but the pipeline is broken if the person leaves, if the person is not there. And if a new person comes, it's totally frustrating to understand. Renku does exactly this. So you can look at this short link, renkulab.io, and then you can see everything, documentation, you can have the code. I think is for free, is gratis. They want to simply know for what case people use, but they are very supportive. And then you can use this to actually keep the pipeline of the data life cycle that I was showing before unbroken, independent of fluctuation in the lab. And the last and most simple concept, if everybody knows this, is so-called GIGO, the GIGO, as we say in Italian, garbage in, garbage out. You can spend a lot of time in designing the most nice workflow, think about Renku, think about all the things. The machine is there, it's perfect polish, but people put garbage in, and then there is garbage out. This is quite obvious. My question is that nobody always answers, and then maybe it would be interesting to discuss about this. I think I have to speed up a little bit. Is that what is bad data? I mean, how can we define bad data? Everybody thinks instinctively, I know what is bad data. So I ask also here the artificial intelligence. This I ask all of them. Well, not all is too much, but I ask 5 or 6 different from ChatGPT, Perplexity, Grok, and others. Now I can look up. And then I try to extract that their answer is what is bad data. Bad data is data that is unfit for use. They agree on this, that inaccurate, incomplete, inconsistent, outdated, arises across the data life cycle, Amper's research decision. I was surprised to see that none of the artificial intelligence told me, this I added the last point, is not reproducible. Basically, if data is generated, but you make another time the experiment and doesn't come, most probably the artificial intelligence doesn't know that this is possible, but as a human scientist, you know that reproducibility is the most important. And we know that we are living in a crisis of reproducibility because many people put data, but they find something is cool, they publish because they are pressure. Good data should be reproducible. And then I asked also the artificial intelligence for dimension, how to evaluate data. And I was given this I think 7 or 6 dimensions. Okay. Now, when you look at true data, this is another comments, you know that don't rely too much on artificial intelligence because there might be so-called hallucination. We think hallucination is something because ChatGPT or the colleagues are stupid. We are not stupid, so we never hallucinate. But as a matter of fact, there is a lot of fraud that are done because people click stuff simply because they hallucinate, misinterpret the data. Now, if I show you this link that are sent by email, mybank2u.com is not the same as mybank2u.com, and citibank.com is not the same. It took me, I had to confess, several seconds, if not minutes, to really understand what is the difference. And the difference there, if I tell you now, I could have made a game, but I have to speed up. The difference is the A, that in the second case is a Cyrillic, is a Russian A, is not the Latin A. With the I, you have, of course, a bias, you interpret, you are smart, and you understand this is AA, so you read my bank and you would click. And the same thing with Citibank. So hallucination can happen also to you. So there might be data that actually you try to see and believe that you see actually what you want to see there. Check if this is really data, because if you put them in a database that people use, then you propagate, this kind of hallucination. Question on the concept? Doesn't seem to be the case, so I try to go quickly toward, well, not so quickly, but okay, I try to stay in the time, to the real world example. And the real world example I will present are essentially 2 or 3, let's say. One is what Swiss Federation, aware of the fact that digitalization published, and I know that people here are not all from Switzerland, but I decided to put this not only for showing what is happening in Switzerland, but also to show how you present a document. And this document, building blocks of data rooms, you can find on the internet. By the way, I make a little bit nasty remark. I want to put a link to it, but the link they have is not fair. You can Google for Bausteine von Datenräumen and then you will find this. But if you try to copy and paste, you get something like the full slide would be full with code and things. So how can I share? How can there is not even an identifier that makes the things. I try all possibility. I try to enter there to look for these things, but still I have a very, very long link. So I didn't put here at the bottom the link. But if you want to look at this document, you will find the PDF. Google will immediately find it. And they organize the document with purpose. Again, when you define your database for data, define the purpose. And the purpose is not right and wrong. It's simply what you want to, what the goal you want to accomplish with this database. So in this case, they give a certain purpose for their public administration. And what is the audience? Who should actually, technician ask me, should we also put the data? We have data from customer, we cannot put there because people, so define who is your addressee, who is and what the purpose of it. What is the strategic goal? Why you're doing this? It's a lot of effort, money and cost. If you do it simply because it's nice and cool, most probably it's a waste of time and money. And focus on interoperability. So just make sure that this thing is a value for all the people in the lab or outside the lab and the people that access it. And then document it, that people can read and then understand, like it's done here. Now in this, I just give you a screenshot. They define in 2 parts, business and organizational blocks with different kind of sub-concept that they define how people should implement digitalization and technical building blocks. The first one thing is that what we want to have as a concept. The second, how do we realize? Remember the information I was giving before, API and so on, no? Okay. The second example is OpenBIS. Actually, this is what I was supposed to speak about, but I kept it a little bit as part of the previous introduction, because the previous introduction, I think, was important to start doing the implementation of OpenBIS. As we started OpenBIS was actually because our management top management told we have to do it, and then we start playing with it. At the moment, we were not aware of all the things I told you before, and we simply use it, and our management decide that we have to use it because it was developed by our neighbor universities, open source, so there was support, was flexible and programmable, was ETL compliant, means that there is a possibility to transfer data very easily in a, like Dropbox. You know, there is a folder, you put data there and the data are automatically uploaded. And if you allow me a language like Trump is enforcing law and order in the lab, no? Okay, let's look a little bit of OpenBIS as it was in the organization I was working in, and then in a sister organization in Germany, BAM and a comparison. Okay, OpenBIS is organized with a hierarchy of 4 blocks. You have to define a space, could be maybe your university or your group. At that case, it was the laboratory, the project. So each project has a separated block, and within this you put data in a record which is an experiment or a collection. And inside the experiment, there are objects. So you have all these tables and things that somehow are connected to one another. And again, spend time in designing. Otherwise, every time everybody design his own way, and in the end, also the naming and so on, it's a mess. I show you here. There is a documentation. I was clicking too fast, so I will not go through the whole things. There are also video online where you can learn about OpenBIS if you want to try it. This is a look inside. I know you can see here. Let me take the laser pointer. Okay, you can see here there is a window, a little bit like Outlook. No, here there is a window where you see all these four hierarchy. You have an inventory with material, with samples, with methods, and then with what is this, publications. Then you have the utilities, and then all the things that you use for your database, and then the thing you want to export. And then in each of them, you put the data, and then you have to decide how you organize. At that time, we decided to organize the discussion, for instance, should we organize by instrument? The data are by instrument, so everybody goes to a specific instrument you find, but this approach is not so efficient for a number of reasons. The best way was to approach, or at least most people was agreeing to use by project. By project sometimes is by people, because a PhD is a person, but it's also a project. But if you will take a technician has several projects. A PhD also has several projects, but typically a subunit of the same main project of the thesis, as long as especially you are behaving fair as a supervisor, making the PhD working only on his own project. Okay, this is just a remark. Please maybe delete this comment. And here is the table that we made. For instance, there was a liquid chromatography MS for chloroparafins or GCMS, and then we were designing chemicals, external chemical, internal chemical, instrument, and so on. All these things are in the publication are discussed. I will show you this publication in the end. So I will not go into the details out of it. I'll just give you the extract of it. And then the second table was the data set of objects that we were linking in it, so the publication data. Another discussion was, should we put all data, all raw data, or only the good data? In the end, we decided to put all the data. Not sure if this is really the best, because the system grows and grows. Sometimes people want to try a little bit, play with the instrument, is not sure if something is at all meaningful before starting a project. In that case, this remains with a decision to put all the data on the instrument. If you want to publish this database, maybe it's good that you kind of select a little bit the data that goes there and put only the data that you have validated. So we made this nice sketch with the process chemical. So you see, this is much, much simpler than the big one that I showed you before. And then I think I have 5 minutes, so I have to hurry up. I talk a lot. I thought that 1 hour was very long. And then the integration with ETL stands for extract, transform, load, basically means having the possibility, like Dropbox, with a folder where people just upload the data there, still manually, and then from there are uploaded into OpenBIS. This is very handy. The effort that we were making here to automate this, that actually the data are automatically extracted from the instrument, and the instrument would write also metadata about the measurement itself. And this is the second example. It's not only to run an instrument, to make the instrument provide data. In this case, this was a big complex setup with a laser, and we wanted also the system to process the data. So I will just jump on it. The idea is that we were acquiring absorption spectrum. I'm not sure with how much familiar you are, but basically the idea was to scan different energy that were pulses of light going through a material. And if the material was transparent, the absorption coefficient signal was low. If the material actually was absorbing, then this will go up And then if the energy is too high, the absorption goes down. So you look for this absorption edge. It is important to understand oxidation and other chemical information. Usually, this kind of measurement you can do only a synchrotron that are difficult to access. You cannot have in your own lab at university. Maybe you can make 1 or 2 measurements per year, but with this setup, we try to allow the same kind of measurement in your own lab. Now, one possibility was to acquire all the data point, which takes time. What happens if your reaction, your sample is changing, like corrosion, for instance, now as a function of time? Maybe you're acquiring here for 1 hour, but in that hour, chemicals and the compound is changing. So this data point refers to a moment of your sample that is very different than this one. So all the thing is biased, it's skewed. The idea is to try to speed up the acquisition and maybe acquire less data point, only the red one here, so undersample, and try to reconstruct the same one. So this is done with a mathematical algorithm. I'll try to explain this very briefly. Imagine that each of these data points is a dimension. So these are energy. Here is energy 1, energy 2, energy 3, and each of these is one axis. So in the end, I can define that this measurement is this yellow vector that plotted on the different axes give the value of the corresponding data point. So in this case, here I would have 500 data point. I will have 500 axes, and each of them give me a value. So this is a collection of data point. If I rotate this vector such that the components are collinear with the yellow one, which is a true one. Now I see only in one dimension, but I can do mathematically in more dimension. I have a lot of zero and maybe few value. So in the end, I reduce the dimension that I need. I make the matrix sparse. This is easily done conceptually, but manually to calculate this thing is extremely complex. So the instrument should calculate during the measurement that I can say, oh no, I'm obtaining a good data. And so this is a little bit in simple terms. And in the end, you can see a comparison. This, I think, was iron oxides, also good for corrosion. And here you see when we were acquiring only 1 point every 6, so 15%, 30%, 45%, 100%, of course, the full range like in synchrotron. And then you see even with 30%, we would able to acquire. So it's possible to make the measurement, let's say, more stupid, so with less data point, but compensate with a loss of complexity of the infrastructure. It's not a synchrotron, it's an instrument in the lab with the data processing that you have in the lab. I hope it's clear, otherwise we discuss. So long story short, what we learned, I need maybe 1 or 2 minutes, sorry, it was a very long. I lost time with the video at the beginning, I regret I did. Okay, I give you my digest. OpenBIS, I believe that is good to enforce metadata templates, automate ingestions to avoid human error, and dashboards, as I showed you before. But I was not very happy because data are encapsulated in own space, and it was not possible to share this with other labs, for instance. If you don't design this from the beginning, that the whole lab are part of the same space. If each lab is the space, then my data could not go to my colleagues. And this is stupid because actually the idea was also to connect this. Naming convention integrated with Renko was not implemented for the pipeline. What I had now is 1 or 2 slides what the colleague at BAM, so similar organization with similar mission in Germany, have found. I will not maybe read everything. I will summarize their lesson learned. First of all, they say centralization is essential. I tend to disagree with it. I say networking of data is important because if you centralize too much, actually one of the best promoting factor of research is the independence. If you start making too many rules top down, then also the creativity is suppressed. The community building is critical. Yes, I said at the beginning, but if you have a very large group of people that have to discuss the design, then it's an endless process. And then phased onboarding works. I think it's important to define the specification from the beginning. So this red point, I think that we don't agree fully, but I understand that point. Then hands-on learning is effective, I agree. Tool integration is a priority. I think it's very important to have a backbone, and then on top of this, people just customize. Schema design needs balance. I agree. Prototypes help to identify gaps. It's interesting to discuss this. And then the organizational lesson stewards, so people that actually are supposed to be implemented, support and recognition. I remember the postdoc that was trying to do was the most hated people in the lab, poor guy. In fact, he turned out to leaving and going in the industry. And I thought, okay, he's the expert, I delegate, he knows what he's doing. But maybe the best thing is to support him and to make sure that he's not alone against the whole lion. Low code access encourage adoption, I agree. And interdisciplinary collaboration yields value, of course, I agree. This will be everything. I have my summaries that I put a little bit like this game with the 10 digital commandments. So the first one is to be fair in the beginning. The second one, to assign globally unique and citable identifiers. The second, index your metadata in a structured and machine-readable way. Then enforce a discipline for naming. Otherwise, everybody gives his own name. And automated Dropbox pipeline. Expose your data to open and programmable API. Be open and non-proprietary format. It's not easy. When you buy instrument, actually the manufacturer already give you in their own format and another manufacturer gives you another format. Control the access with wisdom and granularity. Describe all things with ontologies and shared vocabulary. Integrate instrument with OPC UA so that everything becomes more a network. And then link row to result version all and visualize clarity. I added 13 reading. This is the paper that actually made me come here because Noémie saw this or saw something in LinkedIn.